Okay, I was going to say good morning, but it's not morning anymore. And I was going to tell you I was going to talk fast to get us back on schedule, but we've already blown our complete schedule. So I have no constraints. My name's Richard Lary, and I'm going to talk about something that is not an announced product from XIO. And in fact, the ink is still slightly tacky on the patent applications. So I have to be a little circumspect about what I say, but we have been working for a while on a deduplication, implementation, us and everybody else in the world, and we think we had some interesting ideas on how to do it with performance, and so I want to talk about some of that. Let's get into it. Deduplication requires a lot of work, resources, memory, CPU cycles, disk accesses, inside a storage controller, okay? I mean, on the surface, it wouldn't seem so because all it requires is comparing every incoming piece of data to every piece of data you already own, and how hard could that be? But it actually does require a lot of work. One is, because it's crazy to actually compare the data, everybody uses some kind of signature technique, and signatures are computationally intensive. I'll talk a little bit about that. The other is you need to maintain a large database of signatures, and your data integrity depends on the integrity of that database. So you don't want to cut a lot of corners. Nobody uses a classic database, but it's all database-like in the sense that it's persistent and transactional and all those good things. And when we're talking about potentially petascale systems, you are talking about somewhere between 1 billion and 100 billion entries in your database, which makes it kind of non-trivial. And of course, it must survive power failures and controller failures, must do failover and all the rest of that. And the database access throughput directly affects your write throughput. It isn't the only thing that affects your write throughput. The signatures and a whole bunch of other things dynamic mapping do, but it's an important bound on your write throughput. And usually with databases, you get to use caching, but because signatures are a hash, and hashes are essentially random numbers, people are used to saying, oh, you just throw some cache at it because you cache 10% to 20% of the data, and you get a hit rate of 80 to 90%, and everything's great. Well, with these kinds of databases, you cache 10 to 20% of the data, and you get a hit rate of 10 to 20%. Okay, so it's crappy for caching. The other thing dedupe does is it requires fine grain, depending on the size of your dedupe block, highly dynamic mapping. Every write that comes in can potentially change the map. So you need a high throughput persistent mapping database, in quotes. That is something that people have been doing for a while, although not this high performance. Things like snapshots require the same kind of database, usually on a larger grain. So it's easier, and the main thing is that caching is effective for this because user accesses exhibit locality, and caching 10% of the map will give you 90% cache hits on the map. So, but it's pretty tough, and all the work shows up in writes. All reads do is they follow the map and get the latest copy of the data. And interestingly enough, that's why most deduplication products only publish read benchmarks, so they can show. It's the equivalent of add register to register in old CPU benchmarks, right? It's you're putting your best face for it, but it's not realistic.
Excuse me.
Okay? So we at XIO, we were kind of all old timers when we started, and we've traditionally taken pride in getting high performance out of a modest hardware platform, recognizing the value of a byte and the value of a microsecond. And that's shown up with the fact that our products have many times had the #1 spot in the SPC1 price performance stuff. And we wanted to kind of continue that philosophy into dedupe, because if we don't have to put a 12-core processor into our controllers, it's cheaper controller, right? Even on Excelio, and I'm not announcing dedupe on Excelio, God. But Gus alluded to the fact that Excelio right now uses just the software that's in the Linux stack. So we are a company that produces storage software that goes in our controllers, and this wonderful Excelio box, and we haven't put them together yet. Okay, you can kind of see that coming, that kind of a hyper-converged cluster in a box with all the shared storage and the use of the write-back memory for cache and all blah blah blah. But it's not here. But the minute it is here, if we have a dedupe implementation, people are going to want dedupe on it. Maybe not for their highest performance data, but for the other stuff. And even though you have 44 cores in an Excelio processor, if we use 8 or 12 of them to do dedupe, we're cheating you. That's 8 or 12 processors you can't use. Okay, so less processors, less memory, less IOs is always better if we're doing it. And the important thing to remember about dedupe is it's a space optimization that incurs a performance penalty. So it's a spectrum of implementations. Okay, you obviously have to put in enough energy to get it right, but you can trade off how efficient you are for how much performance you use. And in fact, everybody who's implemented real-time dedupe has made one of those trade-offs immediately, which is that they've chosen a block dedupe rather than a stream variable size dedupe. So that when you edit a verb tense in a Word document, the dedupe copy doesn't only contain the new copy of that word, it contains however much of the Word document actually changed, which is most of it the way, unfortunately, Word structures its objects. All right? And the other thing is that the size of a dedupe block is the most obvious space constraint. The finer grain you make that block, the more duplicates you catch and the more work you do. And that's why a lot of people are implementing 32K and 64K dedupe blocks in their implementations. We have a variable at compile time dedupe block size. Okay, we do our testing at very small dedupe blocks so that we can stress our performance. We don't know what dedupe block size we're going to ship in, but in fact, the more performance you have in your base implementation, the more you can then dial that dedupe block size down and trade some of your performance back for efficiency. Okay? And we won't be talking about that. Although I just did. Sorry for the unpronounceable slide headers, but this is about math. So first I want to talk about signatures. Okay? So dedupe implementations can either use signatures as a proxy for the data, or they can use it as, it's not such a great name, a filtering proxy for the data. Okay? And there are implementations that do both, one or the other out there. A proxy signature is a stand-in for the dedupe block. If the signatures are equal, the blocks are equal. If the signatures are not equal, the blocks are not equal. Okay? That puts a lot of burden on the signatures because, in fact, if two unequal blocks ever have the same signature, you've got data corruption. Okay? So you have to be very careful what signature algorithms you use. Luckily, the crypto community has created a whole bunch of good signature algorithms that, statistically at least, guarantee a very low probability and also are pretty good against a malicious user trying to find a block that has the same signature, right? And they're called crypto hashes. A filtering proxy is a little different. A filtering proxy says if the signatures aren't equal, then the blocks aren't equal. If the signatures are equal, then the block are very, very likely to be equal, but you'd better compare them to check. Okay? So it allows you to very quickly determine the two blocks are not equal, and it takes a little longer to figure out that they're equal.
So is that functions as error code detection at some level? Does it correct the incorrect block, or does it
No. Well, there's
both?
nothing incorrect about either block. It's just that you better not treat them as duplicates.
That's right.
If they're not equal.
Fair enough.
Okay? That's an example of a dedupe system screwing up.
Exactly.
So a false match anywhere in a proxy signature system is a data corruption. Okay? And that's why these systems use the large crypto hashes. A false match in a filtering proxy signature is a performance issue. It causes wasted work. So you want to keep that down, but not, when I was back first designing storage systems back in the 80s, we used 10 to the minus 20th as our threshold for undetected data errors, AKA data corruption, okay? And that was a pretty good number at the time, but systems have gotten a lot bigger and a lot faster. So I picked kind of 10 to the minus 24th now as the threshold. You don't want to corrupt data more often than that, which, by the way, means millions of systems running for millions of years before you see a corruption. On the other hand, here you can relax that constraint a little, and it would be perfectly reasonable to have 1 out of 1,000 matches require you to unnecessarily go to the disk to figure out that the data matches, right? Because it's just performance. So crypto signatures, these are well known, right? You're running them right now on your PC if you're surfing the web while I'm talking. SHA-1, SHA-2, SHA-256 are our current favorites. MD5 is out of favor. People have found some issues with SHA-1, and some of those could compromise its ability to be the wonderful proxy that we want it to be. But SHA-2 and SHA-256 are real solid these days. The problem with all of them is they're very slow, not in network terms. Okay, the processors that you're running on your desktop will keep the network that you have running on your desktop humming at full speed with encryption. But in storage terms, they're real slow. They run at about 11 CPU cycles per byte. And to translate that into terms that are a little more macro, that's about 4 microseconds per kilobyte of data that you sign. Okay, that means that a modern processor, a modern kind of Xeon processor, running full out can encrypt about sign about 250 megabytes a second of data. So if you have an Excelio and it's got 44 cores, it can do about 11 gigabytes a second, which is considerably less than an Excelio is capable of. So these things are CPU bound, right? And in fact, if you want to do just a mere gigabyte per second, which is reasonable from a storage perspective, it'll floor 4 cores, okay? Intel realizes it's a problem and they see a market opportunity and they've come up with some SHA extensions. Unfortunately, they aren't available yet. You can buy them today in the cheapest Intel network processors. You cannot buy them on Xeon, okay? 2018, you will be able to get them on Xeons. But they reduce this by about a factor of 4 or so, okay? Better, not good. Non-crypto signatures, on the other hand, some interesting things have happened too. There have been lots of hashes over time. Back in the late 2000s, a piece of software called Murmur Hash came out and became widely used, and around that time also people started writing hash testers. There's something called Smasher that tests hash algorithms, and Murmur, some later versions of Murmur pass it very well. They're good hashes. It's considerably better. It's what, a factor of 20 faster than a crypto hash, right? Real nice. However, and this is one of the, quote, advantages of being late to the market, in 2015, there was an explosion of non-crypto hash technology led by these guys. Google was actually responsible for a lot of that. They use a lot of hashing. They devoted some effort to it, and they published the results as open source. Thank you, Google. Okay? The best of the standard open source ones is something called Metro Hash. It's real fast. It is not CPU bound. It is memory bound. Okay, and it uses nothing but standard x86 stuff. These guys are faster still, but they require a modern processor with the AES instruction set in it, and they pervert some of the AES instructions to get their speed. Okay, we are currently using Metro Hash because our lab has a selection of hardware in it, some of which is real up to date and some of which is down rev, and we want to be able to run a hash that runs on any Intel processor. So we use Metro Hash today, by the time we do the product, we'll probably switch to one of these guys. These guys are 2 to 6 times faster than Murmur and run at 10 to 30 gigabytes per second. So a processor can flood an Excelio in terms of I/O, right? As I said, one of the benefits of being late to market. So we use a non-crypto signature, and we've also modified it. Since it's making a complete pass over the data, we also can figure out if the data is 0 for free. These algorithms were simple enough that they actually didn't use all the registers in the x86. And so we have a modified version of today Metro hash that signs something and tells you if it was 0. And it turns out that there's a 64-bit and 128-bit version of Metro hash.
So is it a proxy hash or
This is a filtering. We use it as a filtering proxy. We use the 64-bit version of Metro hash, and we throw 16 of those bits away. Because this up here is the formula for data corruption in a crypto hash. Okay, it's a birthday problem.
Yeah.
What's the chance that 2 kids in the room have the same birthday, right? Only expanded out to 100 billion kids.
Right.
And a Google of birthdays, right? And in order to make this work, you need 160 bits in the hash if you really want to keep that data corruption number down to effectively 0. This is the probability of a false filtering match, which only has a performance penalty. Well, if you got 10 to the 11th, that's 100 billion signatures in your system, right? That happens to be about 2 to the 37th. Use a 48-bit hash, that means 1 out of 2,000 signatures will match badly, 2 to the 11th. We can live with that. So in fact, we can get away with a nice cheap 48-bit signature, which means our tables kind of shrink down and our lousy caching becomes more effective because we're caching more signatures, even though we're not caching more data blocks. Okay.
The CPU trade-off is down to 1 core.
And the CPU trade-off is down to a fraction of a core, even for the largest, the highest performance systems. Right, exactly. Okay, let's talk a little bit about the signature database itself. So here's our 48-bit signature. When you're building a database like this and you want it to run really fast, there's only one real choice, and that's a hash on disk, what's called a bucket hash. You hash through a disk block, and you hash inside the disk block, and then you get your answer, right? So we do that. The signature is decomposed. You don't have to hash the signature to use the database. It's already a hash, right? You just pull fields out of it. So we grab a bucket index out of the signature. That takes us to a page somewhere on disk, whatever the page size is. We take inside that, we have a list of probes. One of the important things is this has to be a hash that supports fast deletes, because you're constantly deleting data. Every time you write over a piece of unique data, you have to remove that data from the database, right? So there's a lot of deletes going on. So the classic, I think it's called open hashing, doesn't work because it doesn't support deletes. So we use something where there's an array of probe heads, and then there's a linked list for each probe head, et cetera. And then each hash guy contains the verifier. And one of the nice things about doing it this way, where the key is the data, is we don't have to store the whole key in the data to use as a confirmer, because we know that if you're in this bucket, the low order bits of your signature must be a certain thing. And if you went through this probe head, so the only thing we have to store is the verifier. Our database an entry is 8 bytes. Okay, so we can pack a lot of entries in and keep a lot of entries in memory, even though it may only be 10 to 20% of the total. The problem you have with a bucket hash is what happens when a bucket overflows. Okay, and you can do different things. You can have overflow buckets that you chain to. You can have an extensible or expandable hash where each bucket can kind of split into multiple buckets and all that. And a lot of those things screw up the easy arithmetic of doing things this way, and also screw up one of the things I'll be talking about in in a couple of slides. So we wanted to see how far we could push without having to do those kind of techniques. One, we wanted only a single database reference per signature, okay? And the other is we wanted to have some control, because we do use an expandable hash. We wanted to have some control over when we expand. And so we do something very, very simple. If a bucket is full and you go to insert a signature, throw the signature away, right? It's dedupe, it's an optimization, okay? You can throw the signature away as long as you don't do it very often, right? And so this is where, that's wrong. That's the wrong equation. The equation for this is the standard.
None of us would have.
The mean and standard deviation stuff. Yeah. Signatures are statistically, they're just random numbers, right? You can treat them statistically when you're looking how to build a system as if you had a stream of random numbers coming in, and you assign them to buckets based on their low order bits. So it's kind of like pigeonhole.
So if you throw the signature away,
right,
you're saying that this block, or whatever
block
it is not
unique.
dedupable. It's unique.
Is unique, and
But even-
won't be considered as a duplicate if another block comes in with the same data. There's no data corruption there.
You're kind of converting your data.
You'll never optimize that block
But
out.
I understand this. But you're converting this. I'll call it a data set, right?
Right.
Portions of it will be dedupable. Portions of it are unique data that's dedupable as well, and then portions of it aren't either of those.
Yep. Right. In fact, most writes write unique data, even in a dedupe system, because if you're writing duplicates all the time,
but that unique
what the hell
data,
are you doing?
but that unique data, but that unique data has a signature. It's put in the database and can be used as a duplicate of some other data later down the line.
Right.
This data,
exactly. You're doing it
this
on the
data
top.
cannot be used as any of that.
Right.
Like
It's
most
good
people-
old-fashioned data, unique data, and
But it happens to be in the middle of a data set that could be,
right.
But we don't care. It's just we've
But-
tuned down the optimization possibilities.
we care.
Well,
we care that the data is there.
Do you care if it's in the 4th decimal place for your dedupe ratio?
No.
Good. Good. Let me show you. If you size the table right, you don't have to do anything. You throw the entry away. And the way you size the table right is, as I said, you realize the statistical nature of these signatures, right? And the fact that when you take a bunch of random numbers and throw them into buckets, each bucket, the number of entries in each bucket is a Gaussian curve, right? It's got a mean, it's got a standard deviation, and more importantly, it's got a probability of falling outside of n standard deviations. You remember 6 sigma and all that? So this database is a 4.5 sigma database, which means that as long as the mean plus 4.5 times sigma is smaller than the page size, you don't have a problem. Well, the reason we picked 4.5 sigma, it means 1 out of every 300,000 buckets in the database will be full at any time. So it's the fifth decimal place on your dedupe ratio. And it makes our life easier. It gives us extra performance.
Yeah. I understand all the nice
Right?
things about
It's
it.
a trade-off game. Huh? And so
The data integrity thing
and
that
it turns
gets-
out that it isn't a data integrity issue, because all it does is say, I'm not going to duplicate this guy. In fact, it protects him from data integrity
It's
issues.
the inverse.
You gotta manage all this, different styles of data somewhere.
There
properly.
are, but
Yeah.
we figured the 5th decimal place is not something that people
I understand.
really worry about. If we cared about that, we would have done a stream dedupe, right, and gotten another factor of 2.
Yeah.
For buckets with 500 to 1,000 entries, picking stuff out of thin air, that means you can actually load the buckets to 80 to 85% and still have a 4.5 sigma chance of overflowing. So we do, right? And what we do is we keep track and we say, we seem to have gotten our overflows have passed a certain threshold. It's time to expand double the size of the entire database in an orderly way, in the background, blah, blah, blah. And basically, we take that little line and move it 1 bit over, and we take this little line and move it 1 bit over, and we've still preserved the global nature of that this is a constant decomposition, and we can use it for other features.
You size the hash table based on
We
whatever
have an
your
initial
available
size
storage.
for the hash table,
based on what
and
storage
then
is available.
as we start to get too many overflows, we double it. And when that's not good, or if you add capacity to the system, we might proactively double it.
Okay, that's what I
Right?
was going to say.
So, the other thing I want to talk about, and now this is the right equation, it's the equation for the efficiency of a Bloom filter. A well-sized Bloom filter can.
So what is a Bloom filter?
Huh?
What is a Bloom filter?
I will tell you. Okay, I was going to draw it, but I can't draw, so I will wave my hands, which I'm very good at. A Bloom filter is if you've got a kid and you put a website filter on their computer, right? There are hundreds of millions of bad websites out there, right? How does the server, right, figure out instantly that your kid is going to one of those prescribed websites? It would have to actually do a database lookup for every kid out there who's doing it. Instead, they front their database with a Bloom filter, which allows them to very quickly determine that this website is not a bad website, right? On the other hand, if the Bloom filter says, the Bloom filter only has two answers, no and I don't know.
Yeah.
If the Bloom filter says, I don't know, then they do a database lookup, right? And you can see how that applies to dedupe. But there are other, I think, antivirus programs. You're comparing it against gazillion things of malware. They take really forever. They use a Bloom filter to say, no, that's okay, that's okay, that's okay. Ooh, this needs investigation, right? So here's what a Bloom filter is. It's a huge bitmap, okay? And what you do is you take the thing you're looking up and you create multiple hash functions of that thing. And the number of hash functions that you create is the K in this equation, okay? And you take each one of those hash things, and when you're entering it into the table, you compute K of these hashes, and for each hash, you modulo that hash by the size of the bitmap, and you set the appropriate bit in the bitmap. So let's say K equals 3. You're going to take 3 different hashes of the data, and you're going to set 3 bits in the bitmap, okay? When you want to see if something is in the database or not, you do those same 3 hashes, and you check those 3 bits. And if all 3 bits are set, it might be. And if any of them are clear, it definitely isn't. Okay? It's a very simple construct with some fairly ugly math behind it, but it works very, very well, and it's in wide use. And we're not creating anything new by using a Bloom filter. But a Bloom filter has 2 big issues if you want to do a high-performance implementation. Okay? One, they require you to do multiple hashes of the data, K different hashes, and we've talked about hashes not being cheap. The other is you can't delete from a Bloom filter, okay? So in fact, the good thing about a malware Bloom filter for bad internet sites is they never go away, so you don't need to delete. Okay, same thing with viruses, they never go away. The problem is you're ORing bits into this bitmap, and there's no such thing as an unOR operation. Okay?
XOR doesn't work?
Nope. So the only way to de-OR bits from a deleted entry out of the Bloom filter is to rebuild the Bloom filter from scratch. Take your 100 billion or 10 billion or billion entries and run it back through the process, create the hashes, set the bits, et cetera, on every delete. In fact, what a lot of people who implement Bloom filters do is they allow the filter to get old and crufty. You can leave the deleted data in there, just the efficiency of the filter starts to go down and down and down until it's better to rebuild the damn filter than to put up with its crappy performance, okay? These 2 things make Bloom filters very difficult to use in a deduplication environment. And also, that equation is very nice. You'll notice it has an E in it. That means it was derived from some integral stuff. It used continuous math because Bloom filters are usually huge. And so you can, even though they're discrete things like anything in a computer, you can model them with continuous math because they're so huge that 1 bit is a tiny, tiny fraction of the whole. And that's because Bloom filters are generally very large. We don't use traditional Bloom filters. Instead, we use a buttload of very small bloom filters.
Is that a technical term?
Yes, I was going to use a different technical term, but I realized that we're live streaming.
So you bloom filter at the bucket level?
So, no, at the sub-bucket, way at the sub-bucket level. But yes,
Oh, okay.
So the question is, though, what happens when a bloom filter gets very small? First of all, that equation, the fact that you're modeling it as a continuous thing, that breaks down. It turns out that when you make a whole lot of very small bloom filters, their efficiency does go down. It depends on what you mean by very small, right? In fact, I couldn't find anything in the literature about this, so I wrote a simulator, okay? And what the simulator showed, and I made up this curve for the purposes of this presentation, so don't take it literally, right? Is that you very quickly get down to the baseline efficiency of a huge bloom filter. The reason for the inefficiency is when you pepper this array with stuff, as I said, the number of entries in the array is a Gaussian distribution, right? But this formula is nonlinear.
So how do you
So the guys who are on the right side of the distribution, who have more entries than the average, their performance gets hurt a lot. The guys who are on the left side of the average, their performance doesn't improve so much. Okay? So it's the statistical variability. Well, the bigger the bloom filter size, the less variability.
How do you
the less
determine-
that nonlinearity hurts. Yep.
How do you determine which one of the blumettes, I'll call them, you're hashing into at any point in time?
Next slide. So we call this a bouquet filter because it consists of buckets of blooms. Sorry. And it achieves a false positive rate of, depending on our occupancy, the load factor of the hash table as a whole, which of course when you double the hash table, its load factor goes way down, then it builds back up again, blah, blah, blah. But under 10% all the time, sometimes as little as 2%. Okay? Meaning it eliminates more than 90% of bucket reads for incoming signatures that are not in the database. 98% if you just doubled the hash table size.
Right.
Okay? And as you've noticed here, as you get really down, I mean, I actually said, gee, what if we just had all these 1-bit bloom filters? You can't set 3 different bits on a 1-bit bloom filter. But 32 bits is, 64 bits is about a 20-25% penalty in false positives over a monster bloom filter. 128 bits, you're getting down to a 10% penalty, and then it goes down from there. And I was seduced by the fact that I could implement a bloom filter in a U64 and use CPU instructions to set the bits instead of all this complicated memory stuff. So right now we picked 64 bits. It's easy to change, but so that's the decomposition of the signature for accessing the database. This is the decomposition of the signature for accessing the bloom table. It's the same.
Bits.
It's the bouquet index because a bucket of blooms is a bouquet, right? Then there's a bloom index inside of the bucket, and then there are 3, in this case 6-bit numbers, right? That are the 3 hash indexes into that bloom table. So again, we don't compute multiple hashes because if your signature is worth a damn, if the hash algorithm that you're using for your signature is worth a damn, every bit field in that hash is also a hash.
By definition.
Right? It's uniform, it's random, it's all the good things. So we just decompose it differently. We insert an entry. The bloom filter is in memory. You index into the bouquet and the bloom together. That gives you a U64. You set these 3 bits, you're done.
And so
Okay?
The whole compute cycle, because you just reuse your same data you have coming in.
Yeah, exactly. Performance. Deleting an entry, you zero out the U64, and then you go, notice the bloom index is smaller than the probe index. You go into the probes, you trace those 4 or 8 or whatever many probes belong to that bloom index, trace their indexes, and do the ORs to rebuild the bloom filter. But because there's only 64 bits in the bloom filter, and L, the load factor, has to be small for it to work, you're talking about maybe 3 or 4 entries total. to rebuild the Bloom filter, because how many bits? Each one of them sets 3 bits in a 64-bit word, and it better be mostly zeros when you're done. Huh? So delete is extremely fast from this bouquet filter, right? Because we did the literature search and couldn't find any data on the performance, et cetera, we think we might be the only people using it, so there's that little patent pending thing on
Try
the bottom.
Coho data.
Huh?
Try Coho data.
So is this, okay, we'll check them.
No, data log shipping.
So
it was a little different.
it solves both of the
Similar.
problems. There's single hash, no massive rebuilds. And I got the 5-minute signals, which is good because this is my last slide, and it's about what I'm not telling you. Yeah, I talked fast about Bloom filters, and some of you may have realized that I misled you. I didn't mislead you about how the Bloom filter works. That's all the MS. That's all good stuff. What I misled you is to say that, wow, that Bloom filter, 90% of the time we didn't have to read the database bucket in. Well, that's nice, but if the damn thing wasn't in the database bucket, you've got to add it to the database bucket. So you got to read it in anyway, so what do we save? Right? That's the part I can't tell you.
So there's some magic sauce
Right?
still waiting
That's
to be
That's
revealed.
the other patent that we filed on this stuff. But the key is that deduplication systems waste a lot of resources catalyzing unique user data that will never become a duplicate, and in fact will probably be overwritten before it ever gets a chance to do a duplicate. And remember, when you overwrite a piece of unique data, you got to remove it. Well, that's a bunch of wasted work, right? We have a way to eliminate that work. Okay, we treat unique data differently than we treat data that is known to have multiple copies out on the disk, and that technique shortcuts this wasted effort. And if I say any more, there's a big red button there that somebody's going to hit and the feed will cut off. But it's part of our implementation strategy. The method that we use also has a small, in this case, it's probably not the 5th digit of the dedupe ratio. It's probably the 2nd or 3rd digit
Effect,
of the dedupe
yeah.
ratio effect on dedupe efficiency. But it's a performance wonder, okay? And I'll stop talking now. Thank you very much.
Excellent, thank you.